In this video, we are going to go over problem 1 from our second test. So this problem says that the rigid L-shaped member ABC is supported by a ball and socket joint at A and by 3 cables. So we have 3 cables in this problem. We have cable CD, cable BD, and cable BE. Given that there's a 1.8 kilonewton load applied to F, we're asked to find several things. First, we're asked to draw a free body diagram on the axes provided. I'm going to draw them on some axes that I've drawn below so we can see them a little bit better. Next, we're asked to write the equilibrium equations necessary to solve for the unknowns. So here we're going to have 6 unknowns, so we need 6 equilibrium equations. Next, we're asked to solve those equilibrium equations for the tension in each cable and the reaction at A. So A is a ball and socket, so we're going to have an X, Y, and Z force. Let's start this out by drawing our free body diagram. At F, we have that given force. It's in the Y direction, and it's 1.8 kilonewtons. At A, we have a ball and socket. So we have an AY, an AX, and an AZ force. We have 3 cables. Our free body is the L-shaped member ABC. So all of our forces have to originate on ABC, and our cables pull on the rigid body. So at CD, my cable is going to go from C to D, or my tension is going to go from C to D, and we'll call that TCD. At B, my tension is pulling away, so we have TBD, and here we have our third cable, TBE. So once I've drawn my free body diagram, before I can start writing my equilibrium equations, it's necessary to break up each one of my tension cables into its 3 different components. So my AX, AY, AZ are pretty simple to break up into our components, right? If we drew the AX vector, that's going to be the magnitude AX, 0, 0. Our AY vector is going to be 0, AY, 0. And our AZ vector is 0, 0, AZ. We have that other vector, let's just call it F, that's our given force, and that is 0, negative 1.8, 0. We haven't really been writing out our vectors that are in just one direction like this, but I thought it might be helpful to see these vectors written out like that. So now we're going to focus on our 3 tension cables and breaking them up into their X, Y, and Z components so that we can add them in to our equations. Let's start with that cable TCD. So the vector TCD is going to be the magnitude of the tension in the cable, which is TCD, times the distance that I go in the X direction. So let's look at going from C to D. To get from C to D, first I go this distance, so that's minus 320 in the Z. So I'm going to go ahead and write that in, minus 320 in the Z direction. And then after that, I go positive 240 in the y direction. And once I have gone both of those directions, I'm at D, so I don't need to go any direction in the x direction. So then my x component here is 0. And then all of this needs to be divided by the total length of the CD vector, which is 240 squared plus 320 squared. Which when we solve that out, we get TCD times 0 in the x direction, 0.6 in the y direction, minus 0.8. Note, this is writing out TCD as 3 components, TCDX, TCDY, and TCDZ. Let's color code these like we have above and draw them on our diagram. So this means the vector TCD can be broken up into a y component, TCDY, where TCDY is TCD times 0.6. And we have TCDZ. Where TCDZ is TCD times negative 0.8. So it's pointed in the negative z direction. So this step has allowed us to turn this red vector here into 2 different components, the y component and the z component. We need to do this for each one of our vectors. So next we can do the same thing for TBD. The vector TBD is going to be the magnitude of TBD times how far we go in the x direction. So this one, to get from B to D, we need to go this far in the x direction. So that's going to be minus 420. And then after that, in the z direction, I go this distance. So that is 320 in the negative z direction. And to end up at D, I then have to go 240 positive in the y direction. I still need to divide by the total distance of that vector, so 420 squared plus 240 squared plus 320 squared. If I calculate this out, I get TBD to be the magnitude of TBD times negative 0.72, 0.41, negative 0.55. I can draw those 3 components, so I can replace my red TBD vector with the 3 components applied at B. So I have this going in the positive y direction. That's going to be TBD y, where TBD y is equal to 0.41 TBD. I have a z component, TBD z, which is negative 0.55 TBD. And then I have one more component, which is my x component. That is TBDX, which is negative 0.72 TBD. So this red vector, TBD, on my first diagram is equivalent, so it's an equivalent force system as my three forces applied here, TBD Y, TBD X, and TBD Z. So those three components can replace that vector TBD so that we can add them into our equations. I have one cable left to go. So I have TBE. So TBE is going to be the magnitude of TBE times the distance I go in each of the different directions. So to get from B to E, first I go negative 320 in the Z direction. And then a positive 420 in the X direction. And at that point I'm at E, so I need to go 0 in the Y direction. And then I divide by the magnitude of that line. So I'm left with TBE is magnitude TBE times 0.795, 0, negative 0.61. If you're still having issues visualizing how far we go in each of the directions, another option is to find the coordinates of B and E. So our coordinates of B, we're at 0 in the X direction. We're at 0 Y and 320 Z. E is at 420X, 0 Y, and 0 Z. And now to get our vector BE is going to be E minus B. So in the X direction, we have 420 minus 0, so that's 420. In the Y direction, we have 0 minus 0. And in the Z direction, we have 0 minus 320. Just like we've done in the examples above, we can now break that vector TBE into its two different components. So we have TBE Z. So TBE Z is equal to minus 0.61 times the magnitude of TBE. And then we have the x component, TBEx, where TBEx is 0.795 times the magnitude of TBE. So now that we have all of our vectors, our next step will be to write our 6 equilibrium equations. That will be in the next video that I share.